Good morning, everyone. I am Mr. Ish. Thank you for joining me. We're continuing here with this concept of work and using integrals to do the calculation of work. Because if you have a function which is representing some sort of force, the area below that curve will represent the work. We have to find the work needed to lift a 100-kilogram block by 3 revolutions utilizing a pulley cable system which has no mass. Of course, this is an ideal situation. The pulley, the cable, no friction, no mass, and we're using that system. The pulley has a radius of 0.5 meters. The block we have to lift is 100 kilograms. How do you go about doing it? You're looking at something which looks like this, A to B, and that right there is our formula. The force is coming into play. You know, work is equal to force times distance. We have to have a force component and we have to have a distance component. Let's look at the distance. If I have a pulley system over here, it looks something like this. It has a radius of 0.5. What is a circumference? Well, the circumference will represent the distance involved. Circumference is equal to 2 pi r, which is equal to 2 pi times 0.5, which is equal to pi. But we're doing 3 revolutions of this. We're multiplying this 3, so here's our distance, 3 pi. And we're now looking at it from a resting position where the object was on the ground before it's being picked up, a distance of 3 pi. The force over here is equal to mass times acceleration. We have our mass, 100 kilograms. We have our acceleration, the gravitational constant, 9.8. You'll do 100 times 9.8 dx. Remember, over here I'm already having the entire component of force. All we have to do is integrate this. You're looking here from 0 up to 3 pi. What's 100 times 9.8? It's 980, and then dx. You'll integrate that to be 980x. And then you do 3 pi to 0, and that's not hard. You can do this entirely and bring in a decimal value. 980 times 3 times pi, I'll have 9,236 joules, which if you want you can write as 9.236 kilojoules, and that's the work needed to lift this 100 kilogram block over a distance of 3 revolutions with regards to the radius of that pulley. So this question is done. Let's look at the second, slightly more complex question. We will end the video with this, but this will show you how you can stretch the concept of using integrals for work calculations just a little bit higher. You can stretch it out some more. We have an object here which is being moved, and the movement of that object is being described by this position function 2t cube minus t square. We have to find the work which is done when it is moved 10 meters from a resting position. It has a mass of 10 kilograms. The object is moved very swiftly over 1 second at a time interval of t is equal to 7. It seems like there's a lot going on, but you see the object undergoes its entire movement over a second, but at the time interval 7 with regards to that position function. How will you go about doing it? Think about everything again. Work is equal to force times distance, which is equal to mass times acceleration times distance. We need to somehow figure out acceleration given the position and the time and all of that. Think about it as this way. Force is equal to mass times acceleration, but acceleration is the first order derivative with respect to velocity. You can think of it like this: mass t dv over dt. Acceleration is also the second order derivative with respect to the position, or you can say mass d square s over dt square. These right here represent all 3 equivalent expressions because you're looking at everything with regards to derivative of something. I have a position function. If I were to do its derivative, I'll arrive at the velocity. If I do the derivative, I'll arrive at the acceleration. Acceleration is therefore equal to the second order derivative with respect to the position, and that's all I need to know. That's what I'll do. I'll take that position function and do its derivative twice. I have 2t cube minus t square. When I do the derivative once using the power rule, I'm getting 6t square minus 2t. This right here will be the velocity. When I do the derivative once more, I'm getting 12t minus 2. This here will be the acceleration. Now how do I fit everything in? I have t is equal to 7. My acceleration with respect to time is equal to 12t minus 2. My acceleration with regard to the 7 second time is going to be 12 times 7 minus 2, which will be 82 meters per second square. It's not like we're not talking about here gravity, something falling. It could be something moving horizontally across the ground. You're pulling something, or you're pushing something really hard, or you're shooting something really hard. Anything which would have such a very high acceleration. Here acceleration is 82 meters per second square. Now we have everything we need to take this problem to completion. The integral part is easy. Work is equal to your lower limit is 0, rest up to upper limit 10, You have a mass which is 10 kilograms, you have an acceleration 82. And this is basically completed. 820, you're looking at 0, 10 dx, you're looking at 820 x, 10 and a 0, you're looking at 8200 joules or 8.2 kilojoules. Either of those answers is good, but you see how it was complex, but it went through to completion very quickly once you determined this. And how would you have determined it? By something like this. If your question here involved the velocity function, you'd have just done the derivative of it once and you'd have arrived at your acceleration, then you'd have gone from there. We had a position function, we did two derivatives because acceleration is second order derivative of your position function. We involved the time, 7. What does this mean over here? It means your object moved very quickly over a 1 second interval. But does the coefficient here 1 affect the problem in any way? No, it helps us out because multiplying something by 1 or dividing something by 1 retains that original item. Anyhow, this question is completed for you, and now this video comes to an end. Thank you for watching.